Hello to everybody, microphone active, so let us go. So I want to discuss with you this exercise that I already prepared, which asks to compute this line integral. So it is the integral of the field x cube on the y direction, okay? So first, look at the notation, as I already explained in a previous lecture. This is a way to write down the integral of this field, x cube, in the component j. J is the unit vector on the y-axis, okay? So you have, as usual, to understand it as f, scalar, the vector dx, dy. And so only dy survives if x is x cubed j. Okay? So this is the expression of the vector in coordinates. This is a planar field, so we are in the plane. And the line on which we are asked to integrate is the boundary of this set D, defined as the set of all points whose coordinate have square that can be summed, obtaining a result between 1 and 4. We will see what is this set, but of course we have to specify that this boundary has to be positively oriented, and we want to compute the line integral with two methods directly, so as a line integral like this, and then transforming it into a two-dimensional integral by Green's theorem. Okay? This is the exercise. If it is not clear, stop here and think a bit of it. And now I give you the solution. The solution is written first by clarifying what is D and then what is the boundary of D. Okay? X squared plus y squared is the distance from the origin. So here we are saying that the distance of the origin must be between 1 and 4. Distance of the origin equal to 1 means this circle here, circle of radius 1 and centered at the origin. And squared distance 4 is this one, circle of radius 2 centered at the origin. Okay? And notice that here the boundary gamma is not connected. In a previous lecture I told about simply connected sets, but in this case I'm not talking about simple connectedness, but only on connectedness. Okay? So when I'm talking of connected set, I just mean sets that are made of one piece. And here gamma is made of two pieces. One piece is this, and another piece is this. Okay? So the two pieces of gamma are the two circles. This is the boundary. One circle is larger, it is somewhat external, and the other is internal. So we have to orientate this boundary, which means the union of gamma 1, the circle of radius 2, and gamma 2, the circle of radius 1, both center at the origin. You have to orientate both these components positively. And remember that positively means that if you are here with your bike, and then you take your left arm and you have to fall inside. If you are going positively, you fall in the internal part of of the plan isolated by your curve, in this case by the internal part of this set. So the positive orientation for this gamma 1, the external circle, the external component of gamma, is the usual counterclockwise orientation. Vice versa, we already met this fact, the internal circle is isolating a hole. So in order to fall into the set D, when you are going on bike and you are pushing outside your left hands, this is your left hands, you have to go, in this case, clockwise. Okay? Think again of the bike, or also you can also go on foot, but in general bike is more expressive because you go more precisely on your trajectory. Mm-hmm. And then we can start with the computation, and so you have that the line integral of your field f on gamma means the line integral of f on gamma 1 union gamma 2, which is nothing but the definition of gamma. And of course, when you have to compute a line integral on the union of two curves, this is nothing but the sum of the two line integrals to be computed on the simple elements of the union. Okay? So this is what we have to do. And now we just describe gamma, namely gamma 1 and gamma 2, through components. And this is very easy, this is very usual because we are dealing with circles. So gamma 1 is the circle of radius 2, center at the origin, so you have 2 cosine of t plus 2 sine of t in I and j axis. So in components, this is the circle, and you can write it down like that, and as usual t is 0 to pi. Okay, so here I just wrote in 3 equivalent ways the curve. One is sufficient, you don't have to write it in 3 or more equivalent ways, but I want to make it clear that this notation doesn't change anything, it is always the same. This is written in vector notation, like with the unit vectors y and j on the x and y axis. This is written as a vertical vector, as a so-called column vector. Okay? And here it is written as a row vector, so in general as coordinates. Nothing changes. Choose the one you prefer, the one you understand best, and if you do not have any preference, choose by random. Okay? But it is very, very simple. The message is just everything is correct. Choose whatever you want, provided that you put the correct components inside the vector. Okay. So then let us go to the velocity r dot of the point realizing the parametrization we chose, which means just differentiate component by component. So 2 cos t, once differentiated, gives minus 2 sine of t. 2 sine t gives 2 cos t. So this is the velocity. And then we go to gamma 1 and we compute the integral of your field. So again, it is an integral in the parameter t between the extremes of our parametrization, 0 and 2 pi. Here we have the component 0x cube, which means 2 to the cube 8, cosine of t to the cube, cosine cube of t, dot minus 2 sine t, 2 cos t, and this is equal to what? The product of the two first components gives 0, so it only survives the product of the two second components, and here you have 16. integral from 0 to pi cosine to the 4th power dt, so 16. And okay, in order to compute this integral of cosine to the 4th power of t, you have many methods. Just choose the one you prefer. Okay, here I gave you one method, but there are many others. The problem is that here there is a cosine without sine. So if there were a sine here, the sine is up to the sine, the derivative of the cosine, so you can integrate. Very elementary. But here the method I used, here again, many methods, and choose whatever you prefer. But what I chose here is to decompose cosine to the 4 as a cosine to the square times cosine to the square, that I write here as 1 minus sine square of t. Okay? So in the following passage, I just separate the two terms. In the first integral, we have cosine square, then minus 16 cosine square sine square dt. So I go here with 16, and here I use a formula of duplication of angles. It's a typical trigonometric formula. You can prove it in many ways, or you can send it by heart, as I do, but so it is very natural and it is very easy to use when you have to compute the integrals of cosine square. So we end up with 1 plus cos 2t divided by 2. This is cosine square. And then going to the next term, consider this cos square sine squared and associate to it a factor 4 that we extract from the 16, so we remain here with a factor 4, and we replace this integral through the identity, again a trigonometric identity, 4 cos square sine square. Of course, this is 2 cos t sine t to the 2nd power, and this is sine of 2t squared. Okay, so we end up with 4 sine square 2t in dt. Then in the next passage we integrate this term here. So we have 16. Then we have the first term 1/2 to be integrated between 0 and 2 pi, and of course it is 1/2 times 2 pi, which gives pi. Then in the second term we have to integrate cosine of 2t divided by 2 from 0 and 2 pi. But cosine of 2t is a periodic function of period pi. So because there is 2t. So if we integrate it between 0 and 2 pi, we have to integrate the cosine on 2 periods. But the integral of the cosine, like the sine, on 1 period is 0. So it is like integrating this function, 2 periods. And sorry, this is the cosine, not the sine, so let me do it. Okay, these are 2 periods, and this is the x-axis, and the area here, and here cover 2 bumps, because there is 1 bump and 2.5 bumps, and so equals the area here. So these areas with their sign cancel out each other. The average of the cosine on a period is 0. So here we find 0. And this is a general principle in this sort of computation. You already know it by analysis. One, I probably should not have insisted like that with this explanation, but so we recall it once forever. So here we have minus 4, and again the integral from 0 and 2 pi of sine squared, and again we use this formula of duplication of integrals, and here we have 1 minus cosine of 4t divided by 2, and like before, here we have 1/2 that gives a contribution, 1/2 integrating in 0 and 2 pi gives you pi. So here we remain with -4 pi. And cosine of 40, like before, gives no contribution. So this guy here gives -4 pi. So we end up with 12 pi. And this is the computation that gives you the integral of the field f on the curve gamma 1. Okay? Now we have to compute the same line integral, sorry, not the same line, I mean integral, the same integral of the field f on gamma 2. And notice that this time, okay, gamma 2 has this parametrization, but remember that he has to be run through in the clockwise sense. So let us compare it with gamma 1, if I manage to do that. Okay, here it is gamma 1. So here we have gamma 1, 2 cos t plus 2 sine t on the respective direction y and j. Here gamma 2 is minus cos t minus sine of t. Okay, here it is. Why? Because first, the 2 is not there because the radius is 1, but most importantly there is a minus sign because here we are going clockwise. We are in the internal circle, gamma 2, here we are going counterclockwise. Okay? Here on gamma 1 counterclockwise, on gamma 2 clockwise, in order to preserve the positive orientation. Okay? So this is gamma 2. So this is the velocity of a point running through gamma 2 with the law, with the motion given by the parametrization, and the integral is minus cosine of 4 of t, and not 4 cosine of 4 of t, from 0 and 2 pi, and then we use the same result as before. We just have to divide it by 16. Okay? So it is the same integral as before. But divided by 16. Extremely simple. So before we had that the result was 12 pi, so we divide by 60, so we find 3 over 4 pi, and the result is 45 over 4 pi. It's just a matter of computation. Okay? So this is the first part of the exercise. Look, there is some complication. You have to compute two integrals. These integrals are quite heavy. But now we want to use Green's theorem. So we want to compute the same integral by using the formula. Okay, the formula, I have to write it. And it is the usual Green's formula. So gamma f dot dr is equal to the double integral over d of the derivative with respect to the first coordinate of the second component of the field minus the derivative with respect to the second variable with respect to the first component of the field. And now, again, use Green's theorem. Okay, here I used another notation. However, it is quite clear what is the notation. Fy is f2, and so Fy is equal to x cubed, f1 or fx is equal to 0, so what we find here to be integrated on the region D is 3x to the second power. So we just have to compute this. This guy here, and again, the region D is this region that I colored of some sort of yellow. This is a two-dimensional region which is quite naturally described by polar coordinates. I recall you the polar coordinates are a couple rho theta, such that when you have a point P, let me put the point P here, for instance. It is already occupied by many. So the point P of the plane is here, so the distance from the origin is rho, and the angle with respect to the x-axis is theta, just to be measured on the counterclockwise sense. We already know everything, but I just recall you. So we have this formula for the polar coordinate, x equal to rho cos theta, y is equal to rho sine of theta. Theta in this description of D must go from 0 to 2 pi, because you see D has a sort of circular structure, so every angle from 0 and 2 pi is described here, and rho from 1 and 2. So we write down the integral that we want to compute, and it is 3, the integral of x squared. The integral was of 3x squared. This is equal to 3, and here you have x squared is rho square cos square of theta, but remember that when you pass from Cartesian to polar coordinates, you have to replace dx dy not only with d rho d theta, but you have to multiply by rho. You can also see it by dimensional reason. Here you have a length to the square, and if you keep only d rho d theta, you just have one length, so you have to add another one. But of course, the true reason, this is just a qualitative reason, but the deep reason is given by the formula of the change of coordinate in multiple integrals. So you have 3 rho cube, because rho squared times rho cube cos square of theta, d rho d theta. And so here we have 3 rho cube d rho cos square of theta d theta. And this is a very easy two-dimensional integral because it factorizes. You see, here in the bounds of the internal integral there is no reference to the external variable. So it is just the factorization of two integral. So here you have the factor 3, and then integrating rho, you have rho to the 4th over 4 between 1 and 2 times pi, and this is equal to 3. Here you have 16, 2 to the 4th, minus 1, 1 to the 4, 16 minus 1, divided by 4, multiplied by pi, and again you find 45 over 4 pi. So here you saw that the formulas really work.